Ah, the microwave oven, perhaps the most con of mod cons. Whether you're zapping a mug of lukewarm coffee back to life, rewarming some leftovers, or heating up a frozen burrito for the 4th time this week, this handy little device will get the job done quickly and efficiently without the muss and fuss of a regular stove or oven. But have you ever wondered how this seemingly magical box manages to cook your food without flames or heat, or who invented it in the first place, and why? Well, the answer may surprise you, for the key working components inside this kitchen appliance, found in every kitchen, break room, and hotel suite, was once the most closely guarded military secret in the world, a key technological breakthrough that was instrumental in winning the Second World War and shaping the modern world as we know it. This is the long and surprisingly fascinating story of the microwave oven. Hotels have microwaves in them? That's the most shocking thing from this part for me. I don't think I've ever stayed in a hotel with a microwave in it. Is that an American thing? The origins of the microwave oven stretch all the way back to the discovery of radio waves. In 1865, Scottish physicist James Clerk Maxwell published the groundbreaking paper, A Dynamical Theory of Electromagnetic Fields, in which he postulated that visible light is composed of interacting electric and magnetic fields, and laid out the physical laws today known as Maxwell's equations governing the behavior of these waves. Maxwell's theories predicted the existence of an entire spectrum of electromagnetic waves varying in frequency and wavelength. In 1888, German physicist Heinrich Hertz, whose name is now the official unit of frequency, succeeded in generating and detecting long, low-frequency electromagnetic waves, confirming Maxwell's predictions. Hertz's discoveries not only inspired later inventors like Guglielmo Marconi to develop wireless communications, aka radio, but also laid the groundwork for the discovery of the rest of the electromagnetic spectrum. While the spectrum is continuous, for the sake of convenience, it is usually divided into 7 main regions or bands according to wavelength. Radio waves down to 10 meters, microwaves from 1 meter to 1 millimeter, infrared light from 100 to 1 micrometers, visible light from 700 to 400 nanometers, ultraviolet light from 400 to 121 nanometers, X-rays from 10 nanometers to 100 picometers, and finally gamma rays 10 picometers and below. In the 1910s and 20s, it was discovered that high-frequency electric currents and shortwave radio signals could induce heating in various materials, including human tissue. This led to the development of diathermy, a method for electromagnetically heating muscles and other deep tissues still widely used in physiotherapy to this day. The application of this technology to the field of cooking was readily apparent, and at the 1933 Century of Progress exhibition in Chicago, electrical giant Westinghouse demonstrated the rapid cooking of foods like steak and potatoes by placing them between 2 metal plates attached to a 10 kilowatt, 60 megahertz shortwave radio transmitter. But while impressive, the required equipment was bulky, expensive, and dangerous, and the technique failed to take off. The dream of cooking food rapidly without flames would have to await the development of a revolutionary piece of technology whose invention was driven by the needs not of medicine or gastronomy, but of war. Our story properly begins in 1934, as Europe was once again gearing up for war. The interwar period saw huge leaps in aviation technology, with aircraft going from rickety contraptions of wood, wire, and fabric to sleek, powerful, all-metal machines capable of flying at speeds hundreds of kilometers per hour and altitudes tens of thousands of meters high. So advanced were these new weapons that military planners boasted that the bomber will always get through, and that future wars would be ended swiftly and decisively by destroying the enemy's military and industrial assets from the air. In the United Kingdom, these developments caused a not insignificant amount of anxiety, as the nation had already gotten a taste of the horrors of aerial bombardment during the First World War. Unfortunately, the Royal Air Force's infrastructure for detecting and tracking incoming enemy bombers had barely evolved over the previous 2 decades, depending largely on the human aircraft spotters of the Royal Observer Corps. Sound locating devices called acoustic mirrors were also installed at several RAF bases, but these were of dubious utility. While this equipment could give an incoming aircraft's bearing, it could not measure its range, while the faint sound of distant aircraft was easily drowned out by other noises. Furthermore, as sound travels at slightly over 1,200 kilometers per hour, and even bombers of the era could reach over 400 kilometers per hour, an aircraft's position would have changed significantly by the time it was detected. This forced the Royal Air Force to adopt the strategy of standing patrols, whereby fighters continuously circled likely approach routes to major targets, being relieved by other aircraft when their fuel ran out. As can be imagined, this was a very inefficient strategy, extremely costly in terms of aircraft, engine hours, and fuel. So in the late 1930s, the RAF introduced specialized interceptor aircraft like the Hawker Fury and the Hawker Hurricane, which could remain on the ground and upon receiving an attack warning quickly take off and climb to operating altitude. However, there could never never be enough of these aircraft to cover the entirety of the UK. Some means of detecting incoming aircraft was still needed in order to vector the interceptors onto their targets. Thankfully, a solution soon appeared in the form of radio detection, or RD, what today is widely known as radar. While the invention of radar is typically credited to the British, like all big important ideas, it was actually developed independently in several different countries at around the same time. During his 1888 experiments with radio waves, Heinrich Hertz discovered that these waves could be reflected off metallic objects. Similar effects were later observed by radio pioneers such as Marconi and British engineer Charles Samuel Franklin, who in a 1922 paper delivered before the Institution of Electrical Engineers wrote, quote, "I also described tests carried out in transmitting a beam of reflected waves across country and pointed out the possibility of the utility of such a system if applied to lighthouses and lightships so as to enable vessels in foggy weather to locate dangerous points around the coasts. It now seems to me that it should be possible to design an apparatus by means of which a ship could radiate or project a divergent beam of these rays in any desired direction, which rays, if coming across a metallic object such as another steamer or ship, would be reflected back to a receiver screened from the local transmitter on the sending ship and thereby immediately reveal the presence and bearing of the other ship in fog or thick weather." Indeed, such a device had already been patented in 1904 by German engineer Christian Halsmeyer under the name Obstacle Detector and Ship Navigation Device. Based on contemporary radio technology, the device used a simple high-voltage spark gap and a coherer receiver to project a burst of radio waves and listen for the echo, allowing ships, icebergs, and other hazards to be detected at night or in dense fog at ranges up to 3 kilometers. It could also measure the approximate range of a contact by triangulating the strength of the echoes from various angles. But while now widely recognized as the first practical radar set, unfortunately Halsmeyer's invention failed to attract any military or commercial interest. But in 1933, physicist Rudolf Kuhnholz, scientific director of the Kriegsmarine or German Navy, began experimenting with radio devices for detecting and tracking ships at sea. After some initial failed experiments, he joined forces with amateur radio operators Paul Gunther Erbsloh and Hans Karl Freiherr von Wilhelmsen and formed a private company called GWII. In June of 1934, the company built a 70-watt transmitter and receiver operating at a frequency of 600 MHz and a wavelength of 50 centimeters, and succeeded in detecting large ships in Kiel Harbor at a distance of 2 kilometers. Unlike Christian Halsmeyer's device, the range of contacts was determined by pulsing the radio beam and measuring the time it took for each pulse to travel back and forth. The echoes were also displayed visually on a Braun cathode ray tube. In September 1935, GWII successfully demonstrated their equipment to the Kriegsmarine, who immediately ordered it into production as the SeaTac, the world's first operational shipborne radar. The technology was also later adapted into the Freya early warning radar to defend German territory against enemy bombers. But while the Germans initially led the world in radar technology, development work was ordered halted shortly after the outbreak of the Second World War. This was because German leaders assumed the war would be over in a matter of months. Therefore, advanced technologies like radar and jet propulsion would not be needed. Meanwhile, in Britain, the development of radar was spurred by the most unlikely of circumstances. In 1934, articles appeared in German newspapers claiming that the German military was developing a death ray that used powerful radio beams to shoot down enemy aircraft. Intrigued and apparently desperate for any military advantage, however far-fetched, Dr. Harry E. Wimperis, the Air Ministry Director of Scientific Research, contacted Dr. Robert Watson Watt of the National Physical Laboratory Radio Research Station in Slough and asked him if such a death ray were feasible. Watson Watt passed on the task to his colleague Arnold Wilkins, who later recalled, "I received the request on a piece of torn-off calendar. Watson Watt liked using that sort of thing, being an economical Scotsman. The request, I soon deduced, was to assess the feasibility of a death ray, as he was asking me to calculate the amount of radio energy which must be radiated to raise the temperature of a man's blood to fever heat at a certain distance." End quote. To the disappointment of science fiction fans everywhere, it took Wilkins less than half an hour to calculate that the power requirements of a working death ray were far too high to be practical. However, in his report, he asked if there was anything else the radio research station could do to help the Air Ministry. He soon remembered reading a post office report from the previous year claiming that an aircraft flying across an experimental VHF radio telephone link had caused the received signal to fade, and wondered whether such a radio beam could be used to detect and track aircraft at long distances. Discussing the matter with Watson Watt, Wilkins realized that if they used a radio beam with a wavelength of 50 meters, the 25-meter metal tubing wings of the Handley Page Hayford, the RAF standard bomber at the time, time would act as a half-wave dipole antenna, reflecting back a much stronger signal than previously assumed. Intrigued by this possibility, the Air Ministry Defense Committee commissioned Watson Watt to prepare a scientific report on radio detection, or RD, which he submitted on February 12, 1933, under the title Detection and Location of Aircraft by Radio Methods. In this remarkable paper, Watson Watt not only laid out the fundamentals of radar, but predicted other technologies such as radio-based identification, friend or foe, or IFF systems for aircraft. Impressed, the Air Ministry requested a live demonstration of his theory scheduled for February 16th. In classic British make-do and mend fashion, Watson Watt was forced to beg, borrow, and steal much of the equipment needed for this demonstration. For the transmitter, he used the BBC's shortwave radio station at Daventry, transmitting at a frequency of 6 MHz and a wavelength of 49 meters. And for the receiver, he borrowed equipment built by the radio research station Sir Edward Appleton to study the Earth's ionosphere and packed it into an ancient Morris commercial van. He and Wilkins drove the van to a field outside of the town of Weedon near Daventry, where they set up their receiving aerials. The following day, witnessed by Air Ministry observer A.P. Rowe, the pair hunched over a glowing cathode ray tube display in the cramped van, while RAF pilot Flight Lieutenant F.L. Bluck took off and flew his Hayford bomber at 3,000 meters on a predetermined course between Daventry and Weedon. As the bomber lumbered past at 144 kilometers per hour, the team watched as the glowing green dot slowly climbed up the tube, the signal only being lost when the aircraft was 13 kilometers away. According to legend, Watson Watt triumphantly declared, "Britain is once more an island." With the basic principle of radio detection proven, Watson Watt received £10,000 from the Air Ministry, an enormous sum in those days to further develop the technology. In May 1935, he and his colleagues set up an experimental establishment on an island at Ordford Ness in Suffolk, officially named the Ionospheric Research Station to conceal its true purpose. Progress was incredibly swift. After only a month, the team succeeded in tracking a Western Wallace aircraft out to a range of 27 kilometers, while just a week later, they accidentally detected a flight of 3 RAF Hawker Hart fighters at a range of 32 kilometers and discovered they could track each aircraft individually. The team soon established the optimal wavelength for long-distance detection, 10 meters, and a convenient method for displaying the returned echoes. The cathode ray tube displays were fitted with a time-based circuit that made a phosphorescent dot oscillate rapidly across the screen, forming a horizontal line. Echoes returned from the aircraft would deflect the dot upward, creating peaks along the line. The closer the contact, the further left along the line the peak formed, allowing the aircraft's range to be determined. Altitude was measured by comparing the return of signals to 2 horizontal antennas, one mounted above the other, while bearing was measured by compass returns to 2 crossed aerials. This allowed the position of an incoming aircraft to be determined in 3 dimensions with a high level of accuracy at up to 200 kilometers. However, at the original signal pulse rate of 25 per second, it could not detect aircraft at ranges under 30 kilometers. To solve this, the rate was increased to tens of millions of pulses per second. At this point, the technology was still known simply as radio detection, but American researchers gave it the name Radio Direction Finding and Ranging, or radar for short. With all the technical details worked out, in early 1936, Watson Watt's team began constructing the first operational radar station at Bawdsey Manor in Suffolk, the transmitting and receiving aerials being mounted on 100-meter tall steel and wooden towers. Initially used for technical development and training of future radar crews, in May 1937, the Bawdsey Manor installation became the first site of the Chain Home, or CH radar network, designed to defend England's southern and eastern coasts. By the time it became fully operational in the spring of 1939, Chain Home totaled 20 radar sites stretching from the Isle of Wight to the Firth of Forth. To detect low-flying aircraft, a second parallel network called Chain Home Low, based on gun-laying radar sets operating at a wavelength of 1.5 meters, was also installed. Along with the Royal Observer Corps, Chain Home formed the early warning component of the so-called Dowding system, named after Air Chief Marshal High Dowding, commander of RAF Fighter Command. The coordinates and heading of enemy bomber formations were transmitted from Chain Home and ROC stations to a filter room at Fighter Command headquarters at Bentley Priory in London, where ground controllers, many of them members of the Women's Auxiliary Air Force, or WAAFs, plotted this information on a giant map and guided the appropriate fighter units to make the interception. By providing early warning and directing aircraft to specific targets, the Dowding system allowed Britain's limited fighter force to be deployed with maximum efficiency and effectiveness. Compared to contemporary German and later wartime designs, Chain Home was relatively primitive and inefficient. Instead of mechanically scanning a narrow beam, it projected a giant floodlight across the entire sky, a system which consumed huge amounts of power. Despite this, however, the network used readily available technology, allowing it to be made operational just in time for the outbreak of the Second World War, a fact which would soon grant the British an enormous strategic advantage. Meanwhile, the Germans watched with curiosity as the Chain Home towers began popping up along the the English coast. While they assumed they had something to do with aerial defense, the stations looked so different from German designs that they could not be certain. So, in the spring of 1939, General Wolfgang Martini, head of the Luftwaffe Signals Branch, ordered the mysterious towers investigated. For this mission, he commandeered an unusual vehicle, the LZ-130 Graf Zeppelin, the last German rigid airship and the sister ship of the ill-fated Hindenburg. Fitted with signals intelligence equipment, Graf Zeppelin left its hangar in Frankfurt on July 12, 1939, and headed to Bordsee on the English coast, cruising just out of sight of the experimental station. Yet instead of the pulsed radar signals they were expecting, the German radio operators just heard random static. No matter how they adjusted their equipment, they could detect nothing. After cruising up and down the English coast for several hours, the airship gave up and returned home empty-handed. She returned early the next month on another spy mission, but was equally unsuccessful, leading the Germans to conclude that the British had no working early warning system. Of course, Chainholme was in fact fully operational, and its operators accurately tracked the giant airship throughout its 2 spy flights. So why didn't Graf Zeppelin detect their signals? Well, the simple fact was that German radars worked at wavelengths of around 50 centimeters, and they expected the British equipment to be similar. But Chainholme worked on a much longer 10-meter wavelength. The Germans simply hadn't set their detection equipment to detect the right frequencies. This oversight was to have dire consequences in the summer of 1940 when the Luftwaffe set out to destroy the Royal Air Force on the ground and force the British to negotiate peace terms, an aerial struggle now known as the Battle of Britain. Though early in the battle, the Germans made some dive bombing raids against the Chainholme radar stations, this campaign was half-hearted and quickly abandoned. Not only did the Germans fail to recognize the vital importance of the stations, but the installations themselves proved difficult to attack, and any damage inflicted was quickly repaired. This failure was to cost the Germans dearly, for aided by Chainholme and the Dowding system, within 2 months our Air Fighter Command succeeded in chasing the Luftwaffe out of the daylight skies, shooting down 1,736 German bombers and fighters at a loss of just 915 British aircraft. The Germans thus switched to making nighttime raids against civilian centres like London, Liverpool and Coventry, kicking off the infamous Blitz. Developed just in the nick of time, the Chainholme radars played a vital role in saving the Royal Air Force from destruction and allowing Britain to survive to fight another day. But as the first phase of the Battle of Britain drew to a close, the system began to show its major shortcomings. While Chainholme and the Dowding system could track incoming enemy aircraft and vector fighters onto an interception course, the actual interceptions had to be made visually. However, when the Germans switched to night bombing, this became all but impossible, and for the first few months of the Blitz, Britain's air defences proved all but useless against the nocturnal intruders. Solving this problem would lead to one of the greatest technological breakthroughs of the entire war. Meanwhile, the RAF's Bomber Command turned the tables on the Germans and began flying regular bombing raids on Germany and occupied Europe. But just like the Germans, the British quickly discovered that bombing in daylight was suicide, and atrocious losses at the hands of the Luftwaffe fighters forced them to switch to night bombing. However, this created problems of its own, as navigating to a target and dropping bombs accurately in pitch darkness proved all but impossible. Indeed, in the early days of the bombing campaign, it was determined that over 90% of bombs fell on open countryside several kilometers from the intended target. Even worse, by this time, the Germans had recognized the utility of radar and developed their own, even more sophisticated version of the Dowding system, known as the Himmelbett, or 4-poster-bed, or the Kammhuber line, after General Major Joseph Kammhuber. Early warning of incoming enemy bombers was given by a chain of coastal radars codenamed Freya, after the Queen of the Gods in Germanic mythology, operating at a wavelength of 1.2 meters. Once the bombers had passed the coast, they were handed over to a network of smaller radars codenamed Wurzburg, operating at a wavelength of 50 centimeters, which could accurately track individual bombers and direct searchlights, anti-aircraft guns, and night fighters toward them. As in the Dowding system, all of this was coordinated from central command rooms largely staffed by female auxiliaries known as the Luftwaffe Helferin. At first, German night fighters, like their British counterparts, had to make the actual interceptions visually, but from 1942 onwards, they were increasingly equipped with the 61-centimeter FUG-202 Liechtenstein Airborne intercept radar, whose distinctive branching aerials mounted to the aircraft's nose were nicknamed mattress or stag's horns. The technical details of the Kammhuber line, which inflicted unsustainable losses in the early days of the night bombing campaign, were soon worked out by British intelligence by various methods, including signals intelligence, aerial reconnaissance photographs, the breaking of the German Enigma cipher, and even a daring raid on February 27, 1942, codenamed Operation Biting, in which a team of British airborne troops parachuted into a Wurzburg site in Bruneval in France to capture pieces of the radar and some of its operators, but that's a story for another video. Once the British knew how the system and its various components worked, they very quickly set about developing countermeasures. The first of these was simply to form the bomber force into a single concentrated stream and fly them through a single point in the Kamm-Huber line, swamping the Würzburg radars and preventing night fighters from being accurately guided towards individual targets. However, the Germans quickly countered this tactic by deepening the line to include multiple overlapping defensive sectors and placing large radar-controlled anti-aircraft batteries around major industrial targets like factories. Undeterred, the British turned to a series of increasingly sophisticated electronic countermeasures. The first of these, codenamed Tinsel, Jostle, and Airborne Cigar, jammed night fighters' radios by broadcasting white noise generated by microphones placed in the attacking bombers' engines, preventing ground controllers from guiding them to an intercept. Later, when night fighters began being equipped with Liechtenstein airborne radar, another jamming device, codenamed Pipe Rack, was developed to counter it. Mandrel was used to jam the Freya early warning radars. Moonshine was a transponder which made a single decoy aircraft appear on radar like an enemy flight of bombers, luring German air defenses away from the main force, while Perfectos triggered the night fighters' identification, friend or foe, or IFF transponders, revealing their positions. Rather more devious and amusing was Operation Corona, in which German-speaking radio operators aboard the bombers impersonated the German ground controllers, causing mass confusion among the night fighter force. After learning of this deception, the Germans switched to using female ground controllers, assuming that the RAF would not send WAFs up in operational aircraft. But the British were already one step ahead and had set up a team of German-speaking WAFs at a high-powered transmitting station at Hollywood Manor in Kent. This scheme often resulted in darkly hilarious scenes, as one WAF, Ruth Tosek, later recalled, quote, "They would say, 'Das ist ein Feindsteamer,' an enemy voice, 'Don't listen to it, don't listen to it.' And we would reply, 'Sie sind die richtige Stimme.' We are the real voice." This would go on until the pilot became completely confused and didn't know who was who. But the most effective Allied radar countermeasure was ironically the simplest. Codenamed Window, this consisted of strips of aluminium foil cut to half the wavelength of the German Würzburg radar, 26.5 centimeters, creating a half-wave dipole antenna that would radiate back a much stronger echo than a random aircraft signature. Dropped in bundles from attacking aircraft, Window completely overwhelmed the radars, rendering them useless. Indeed, so effective was Window that for months the British hesitated to deploy it, fearing that the Germans would quickly copy it and retaliate in kind. Ironically, the Germans had developed an identical weapon codenamed Dupel, but also hesitated to use it for identical reasons. However, RAF Bomber Command losses soon became so high that Prime Minister Winston Churchill ultimately gave the order to open the window. The first large-scale operational use of this doomsday weapon was during Operation Gomorrah, the 24th of July 1943 firebombing raid against the port city of Hamburg. As expected, Window proved devastatingly effective, completely blinding the German defenses and leaving searchlights, anti-aircraft guns, and night fighters to grope uselessly around the night sky. This allowed the 746 bombers to reach the city almost unopposed and deliver their deadly payloads. The summer of 1943 had been unusually hot and dry, turning Hamburg into a tinderbox and allowing the incendiary bombs to touch off a gigantic firestorm, a self-sustaining flame tornado that generated winds of up to 240 kilometers per hour, sweeping citizens off their feet like dried leaves and sucking the air out of air raid shelters. The raid destroyed 61% of Hamburg's houses and killed 51,000 of its citizens for the loss of just 12 RAF aircraft. Indeed, afterwards, Albert Speer, Hitler's Minister of Armament, stated that if raids of similar size had been conducted against just 5 more major German cities, the Allies could have won the war in 1943. With their radar network rendered ineffective, the Germans switched to a tactic codenamed Wild Sow, or Wild Boar, in which night fighters flew above the enemy bomber streams and made their interceptions visually by spotting their targets silhouetted against the searchlights and fires on the ground below. Later, they also developed systems called Wurslaus and Nuremberg that could distinguish between moving bombers and stationary clouds of Window, or detect the specific reflections produced by spinning aircraft propellers. Night fighters were also equipped with Liechtenstein SN2 and Neptune radars operating at frequencies immune to Window in the Flensburg and Naxos devices, which allowed the fighters to home in on Allied bombers' Monica tail warning radar and the H2S ground scanning radars. These advancements allowed the Germans to resume inflicting heavy losses against Allied bombers starting in early 1944. As a result, the Allies were forced to remove Monica from their aircraft and only turn on their radars at the last possible moment. But if the Germans ever considered retaliating against Britain using Dupel, they would have found this countermeasure wholly ineffective thanks to a key technological breakthrough, a device capable of producing extremely short-wave centrometric radar beams. The development of this device was initiated by the Royal Navy, which wanted a more precise radar to allow warships and patrol patrol aircraft to detect small targets like surfaced U-boats and aim their guns in poor visibility at long distances. In 1939, the Admiralty contacted a team at the University of Birmingham under Dr. Marcus Oliphant, who would later play a key role in the Manhattan Project that developed the atomic bomb. Oliphant assigned the task of developing centimetric radar to research fellow John Randall and postgraduate student Harry Boot, who began experimenting with a device known as klystron. Used in many early radar sets, the klystron was a type of amplifying vacuum tube that bounced a beam of electrons between two resonant cavities, creating an oscillation that generated high-frequency radio waves. Unfortunately, klystrons could only generate practical radar beams at wavelengths down to 50 centimeters. At shorter wavelengths, the power requirements became impractically high. Randall and Boot thus abandoned the klystron and focused on another device known as the split anode magnetron. In November 1939, the pair sketched out an unusual device they dubbed the cavity magnetron. This consisted of a solid cylindrical anode made of copper with a central cavity and 6 smaller resonant cavities arranged around it and connected by slots. A cathode injected electrons into the central cavity, while a powerful magnet caused the electron beam to swirl around its edge past the openings to the peripheral cavities, creating a resonance in a similar manner to blowing air across the mouth of a bottle and hopefully generating wavelengths of 10 centimeters or less. When Randall and Boot presented their concept to Oliphant, he was not overly enthusiastic, but given the discouraging lack of success with other approaches, he tacitly approved their experiments. With resources almost non-existent, Randall and Boot were forced to resort to the string and sealing wax approach that had characterized British physics for over 100 years. High-voltage transformers were scrounged from the Royal Navy base at Portsmouth, while an old teaching electromagnet was unearthed in one of the university labs. Other components like the copper anode and high-voltage rectifiers, Randall and Boot manufactured themselves. Emblematic of the make, do, and mend nature of the endeavor, the ends of the prototype were vacuum sealed using 2 halfpenny coins and sealing wax. The methods used to test the exotic new device were equally crude. To measure its power output, Randall and Boot connected the magnetron to a series of light bulbs, increasing the power until the bulb burned out before swapping in a new one. By this method, they measured the maximum output to a whopping 400 watts. To measure the emitted wavelengths, they used an apparatus known as a Lecher line, a pair of parallel wires attached to the magnetron along which a light bulb could be slid, the bulb lighting up at each half wavelength. To the pair's astonishment, their first prototype produced a wavelength of 9.87 centimeters, almost exactly what they were aiming for. News of the breakthrough at the University of Birmingham spread like wildfire through the British military establishment, who immediately ordered that top priority be given to its refinement and deployment. By June 1940, the General Electric Company laboratories in Wembley, Essex, had developed the NT98, the first practical mass-produced air-cooled cavity magnetron light enough to be installed in aircraft. These early magnetrons suffered from the problem of random frequency jumping, but this was soon solved by Dr. J. Sayers by strapping alternate resonance cavities with heavy copper wires. So urgent was the need for these magnetrons that the first production models were manufactured in great haste using a drilling jig made from a Colt revolver cylinder. In August 1940, with Britain under threat of Nazi invasion, a delegation of scientists known as the Tizard mission traveled to the United States, bearing Britain's most important technical breakthroughs, including an early production cavity magnetron. This gift allowed magnetrons to be mass-produced in American factories and opened the doors for further exchanges of key military technology. It's difficult to overstate the importance of the cavity magnetron to the course of the Second World War, with this now largely overlooked breakthrough ranking higher than more well-known technical developments like jet propulsion or the atomic bomb. Indeed, American historian James Finney Baxter III later declared the magnetron to be the most valuable cargo ever to reach these shores. In late 1941, British Bristol Beaufighter night fighter aircraft began being equipped with the Airborne Intercept or A1 Mark 7 radar, which produced a narrow 25 kilowatt beam with a wavelength of 9.1 centimeters that could accurately pinpoint enemy aircraft in pitch darkness at a range of between 120 meters and 10 kilometers. Previous Airborne Intercept radars operating at wavelengths of 1.5 meters were plagued by random echoes from the ground below, limiting their effective range to around 5 kilometers. This technology allowed the Royal Air Force to finally sweep the Luftwaffe from British skies, bringing the dreaded Blitz to an end. Meanwhile, centimetric radars fitted in Royal Navy and RAF Coastal Command aircraft like the Vickers Wellington, Consolidated B-24 Liberator, and Consolidated PBY Catalina allowed them to detect even the periscopes of submerged German U-boats. Previously, these aircraft were fitted with the less sophisticated Air-to-Surface Vessel or ASV Mark II radar, operating at a wavelength of 1.25 meters. While these sets allowed aircraft to detect a surfaced U-boat at a range of 100 kilometers, the Germans soon developed a detector called METOX that allowed them to crash dive and escape before an attacking aircraft came into firing range. With the introduction of the magnetron-based ASV Mark III, however, the U-boats had nowhere to hide and were forced to spend more and more time submerged, greatly reducing their effectiveness. More than any other breakthrough, the cavity magnetron helped turn the tide of the Battle of the Atlantic, the longest fought of the entire war, and the only one which Winston Churchill admitted truly frightened him. The magnetron also played a major role in Allied strategic bombing against Germany and occupied Europe. As previously mentioned, when the British switched from daylight to night bombing early in the war, they discovered that accurately reaching and bombing specific targets using traditional methods like celestial navigation and dead reckoning was all but impossible. RAF bomber commands thus switched from precision bombing of industrial and military targets like factories and airfields to a strategy of area bombing with incendiaries against large population centers. They also copied the Pathfinder strategy pioneered by the Luftwaffe during the Blitz, wherein an elite group of aircraft with highly skilled navigators flew ahead of the main bomber force to mark the target with flares and incendiary bombs. To further increase their accuracy, the Pathfinders soon adopted a variety of electronic navigation aids, another technique copied from the Germans. The first of these, codenamed GI, was introduced operationally in 1942 and consisted of 3 transmitting stations designated A, B, and C, spaced around 160 kilometers apart. These stations transmitted synchronized pulses such that, depending on his position, an aircraft navigator would receive the pulses from one of the stations ahead of the others. If all the points where all 3 signals were received simultaneously were plotted, they formed long hyperbolic curves known as isochrones, similar to the isobar pressure lines on a weather map. These curves intersected with each other at certain points, forming a huge grid projected across the European continent, hence the codename G for grid. Against this grid, aircraft could fix their position. The great advantage of G was that it was entirely passive, the receiving aircraft emitting no signals which could give away its position and could be used by any number of aircraft at once. Also, unlike German beam systems, it gave no indication as to the target of a particular raid. G inspired the creation of a similar American system known as LORAN, or Long Range Navigation, which remained in use until the 1980s as a general maritime navigation aid for personal and commercial vessels. However, while G could get a bomber to a particular city, it was not accurate enough to guide it over a specific target like a factory, and had a maximum range of 250 kilometers, too short to reach the heart of Germany. Consequently, in early 1943, the British developed a more sophisticated system codenamed OBO. Unlike G, OBO was an active system incorporating a special transceiver aboard the aircraft which received and returned signals from a pair of transmitting stations in Britain. The first, dubbed CAT, kept the bomber flying along a circular course intersecting with the target. If the pilot drifted off this course, he heard a string of Morse code dots or dashes in his headphones, as in the ubiquitous Lorenz blind landing system, prompting him to correct left or right. Meanwhile, the second station, codenamed Mouse, kept track of the bomber's position and sent a signal when it was over the target, automatically triggering the release of the bombs. The accuracy of OBO was around 100 meters at 400 kilometers, enough to hit a factory in Germany's industrial Ruhr area. However, it could not reach as far as Berlin, and being an active system, gave off signals that German night fighters could home in on. The British thus set about developing a self-contained navigation system whose reach would only be limited by the range of the aircraft carrying it. This system took the form of HS2, a modified version of the Airborne intercept radar pointed downwards, allowing ground features like coastlines, rivers and canals, and towns to be identified in pitch darkness or through thick cloud. This was accomplished using a rotating parabolic antenna caused in a streamlined radome and a circular plan position indicator with a persistent phosphor that refreshed itself with every rotation of the cursor, the classic image of a radar screen that we're all familiar with today. The system was originally named BN for blind navigation, but it was soon renamed H2S, the chemical formula of the pungent gas hydrogen sulfide, allegedly after a comment made by Professor Frederick Lindemann, scientific advisor to Winston Churchill, quoting him here. It was stinking because it ought to have been done years before. Interestingly, the RAF was initially hesitant to deploy H2S since it was feared that the Germans would capture and copy the top-secret magnetron technology. Indeed, experiments had proven that the copper anode at the heart of the magnetron was virtually indestructible and would likely survive even the most violent crash or self-destruct charge largely intact. Technicians were thus assigned to develop an alternate version using the well-known klystron tubes, but this proved technically infeasible. In the end, the strategic benefits of deploying H2S were deemed to outweigh the risks, and the system was first deployed on a mission in January 1943, when Short Sterling and Handley Page Halifax bombers of 7 and 38 squadrons successfully located and marked the city of Hamburg in extremely bad weather. H2S played a vital role in the latter stages of the Allied bombing campaign in Europe, while a similar blind bombing radar called the AN-APQ-10 was was used by American Boeing B-29 Superfortress bombers against targets in Japan. As predicted, the Germans did manage to capture and copy magnetrons from downed Allied aircraft and produce their own centrometric airborne intercept radar, codenamed Berlin, but these did not see service before the war ended. One of the Allies' greatest secret weapons, the cavity magnetron made an outsized contribution to the war effort, likely shortening the conflict by several years. This is particularly impressive given that Randall and Boots' original prototype, including the halfpenny pieces used to seal the ends, is estimated to have cost only £200, a bargain by any measure. Other radar technology played a similarly key role in the conflict. For example, tiny radar sets, known as proximity fuses, were placed inside anti-aircraft artillery shells, allowing them to explode when they passed close to a target. Such fuses were vital in allowing the US Navy to fend off Japanese kamikaze suicide attacks and the British to defeat the German V-1 flying bomb or Doodlebug. And for more on this incredible battle, please do check out our previous video, Wingtip and a Prayer, the insane way British pilots defeated Germany's secret weapon. And radar altimeters based on tail warning radar sets were used to detonate the 2 atomic bombs dropped on Hiroshima and Nagasaki, helping to deliver the killing blows that finally brought the war to an end. Now, by this point, you're probably thinking, what the does this have to do with microwave ovens? Well, as you'll recall from the very beginning of the video, microwaves are defined as electromagnetic radiation with a wavelength between 1 meter and 1 millimeter, exactly the kind of radiation generated by a cavity magnetron. But while experiments with cooking food using shortwave radiation had been conducted before the war, it took a happy and hilarious accident for the wartime sword of radar to be beaten into the peacetime plowshare of everyone's favorite kitchen appliance. In 1945, Percy Spencer, an engineer at the Raytheon Company in Cambridge, Massachusetts, was working on the magnetron of an active radar set when he reached into his pocket for a snack. To his surprise, he discovered that his Mr. Goodbar chocolate bar had somehow melted into a sticky mess. This effect had been observed by several other technicians, but Spencer was determined to know more. He thus embarked on a series of legendary experiments, as recounted in a 1958 Reader's Digest article. He sent a boy out for a package of popcorn. When he held it near a magnetron, popcorn exploded all over the lab. The next morning, he brought in a kettle, cut a hole in the side, and put an uncooked egg in its shell into the pot. Then he moved a magnetron against the hole and turned on the juice. A skeptical engineer peeked over the top of the pot just in time to catch a faceful of cooked egg. The reason? The yolk cooked faster than the outside, causing the egg to burst. These experiments confirmed that it was indeed the microwaves emitted by the magnetron, and not something else like radiated heat, that was heating up the food. Today we know that microwave ovens work because the constantly changing electromagnetic field causes molecules like water and fat with a strong dipole structure, that is, one negatively and one positively charged end, to rotate rapidly, generating heat that is transferred to the rest of the food. This is why dry, low-fat foods like crackers don't heat up when placed in a microwave. Contrary to popular belief, however, microwaves don't cook food from the inside out. Rather, this effect occurs when there is a greater concentration of absorbent moisture inside the food than on its surface, such as in the classic hot pot with its tongue-searing molten lava filling. Also, microwaves emerging from the magnetron bounce around randomly inside the oven and interfere with themselves, producing zones of varying power density that can cook different regions of a food item at different rates. However, this effect is usually countered through the use of a turntable to slowly rotate the food, or a motorized waveguide to more evenly distribute the microwaves around the interior of the oven. While Spencer's supposedly serendipitous discovery has become the stuff of legend, in reality, the development of the microwave oven was a gradual process involving dozens of small discoveries and developments by multiple technicians. Nonetheless, on October 8, 1945, Spencer filed US patent 2,495,429 for a method of treating foodstuffs, in which he outlined basic technical details such as the optimal frequency, 2.45 gigahertz, power, and cavity size for effective cooking. Alarmingly, the oven design in his patent featured a conveyor belt for moving food past the magnetron and open ends which allowed face-melting microwave radiation to leak out of the appliance. In a follow-up patent filed in 1949, Spencer described the now ubiquitous process of microwaving popcorn, while in a 1951 patent, he described how to broil a lobster in a microwave by shoving a pencil-like rod up its behind to prevent the tail from curling and becoming harder to cook, as if lobsters didn't have it hard enough already. Based on the work of Spencer and others, in particular engineers Lawrence Marshall, Fritz Gross, and Marvin Bock, in 1947, Raytheon produced the first prototype microwave oven, the first of which was installed in a Boston restaurant for testing. Another prototype was incorporated into a delightfully named Speedy Weenie vending machine in New York's Grand Central Terminal, which dispensed freshly microwaved hot dogs. Later that year, Raytheon finally launched the world's first production commercial model under the brand name Radar Range. But But while today we think of microwave ovens as compact, convenient countertop appliances, the first radar ranges were absolute behemoths, standing at 1.8 meters tall and weighing 340 kilograms. They consumed 3 kilowatts, 3 times as much as a modern microwave, and produced so much waste heat that they had to be water-cooled. With an eye-watering price tag of $5,000, that's $68,000 in today's money, these units were far out of reach of the average consumer and were instead intended for use in restaurants, cafeterias, airliners, and ships' galleys, with one example being installed aboard the revolutionary nuclear-powered cargo ship and passenger liner MS Savannah in 1961. In 1955, Raytheon licensed its microwave technology to appliance manufacturer Tappan, who introduced the first microwave oven designed for consumer use, the RL1. Designed to be mounted to the wall like a conventional oven, the RL1 still cost a whopping $1,295 or $11,000 in today's money, resulting in disappointing sales. But technology was rapidly improving, and soon more reasonably priced models with lighter, air-cooled magnetrons began to appear on the market. In 1964, the Sharp Corporation of Japan introduced the first microwave oven with a rotating turntable to address the traditional problem of uneven heating. And at around the same time, the Litton Company developed a magnetron that could survive a no-load condition, that is, running with nothing in the ovens to absorb the microwaves, making microwave ovens much safer and long-lasting. Finally, in 1967, the Amana Corporation, a subsidiary of Raytheon, introduced the countertop radar range, the first compact microwave oven as we would recognize it today. The model took an unusual approach to promoting even food heating, using a rotating waveguide or mode stirrer to distribute the microwave beam, allowing the food to remain stationary. With a price tag of $495 or $5,000 in today's dollars, it was still very expensive. But with simplified designs and advances in manufacturing techniques, the price gradually fell, and throughout the 70s and 80s, microwave ovens began to be found in more and more homes. Indeed, while only around 40,000 microwave ovens were sold in the United States in 1970, by 1975, this number had risen to nearly 1 million. And while only 1% of American households owned a microwave oven in 1979, by 1986 around 25% did. By 1997, this figure had risen to an astonishing 90%. With the exception of Japan, where the popularity of microwaves benefited from simpler and cheaper to manufacture magnetron designs, adoption has been slower elsewhere in the world, with 88% of Canadian, 65% of French, 5% of Indian, 40% of Russian, 38% of South African, and 16% of Vietnamese households owning a microwave oven by the turn of the 21st century. And as microwave ovens became increasingly popular, manufacturers began adding additional features. For example, in the early 1970s, Tappan began offering hybrid models that incorporated both microwave capability and conventional oven heating elements. In 1975, Amana introduced the first automatic defrost feature with their RR4D model, while the following year, their RR6 model incorporated the first fully digital microprocessor-controlled control panel. Since then, microwave ovens have more or less settled around a standard design, with different brands or models differing largely in their styling, control panel layout, and number of cooking modes like defrost, popcorn, etc. Indeed, as of 2020, nearly all microwave ovens sold in the United States, regardless of brand, are manufactured by a single company, the Midea Group, headquartered in Beijing in China. Most consumer microwave ovens consume between 600 and 1200 watts of power and operate at the same 2.45 gigahertz frequency established by Percy Spencer in 1945. As many telecommunication companies operate at microwave frequencies, in 1947, Raytheon and General Electric petitioned the Federal Communications Commission, or FCC, to set aside a section of the electromagnetic spectrum for use by microwave ovens, medical diathermy machines, and other specialized equipment so as to not interfere with vital communications networks. The two allocated frequencies, 915 ± 25 MHz and 2450 ± 50 MHz, are today known as the Industrial, Scientific, Medical, or ISM bands. The 915 MHz frequency is commonly used by industrial microwave ovens as the longer wavelengths penetrate deeper into the food and raise its temperature faster, speeding up the overall cooking process. Interestingly, no matter how many power or specialized cooking settings a microwave has, the magnetron always operates at a constant power output. Different heat settings are thus achieved through duty cycling modulation, i.e. switching the magnetron on and off for a different period of time. This way, the rate of total amount of energy deposited into the food can be controlled. For example, if a microwave is set to half power, then the magnetron would be switched on only half the time. Similarly, since ice absorbs microwaves less efficiently than liquid water, the defrost setting keeps the magnetron switched on for even less of the total cooking time, allowing the food to defrost slowly without overheating and prematurely cooking it. By contrast, inverter microwaves use solid-state switching gear as opposed to the traditional transformer and electronic relay, allowing them to operate the magnetron continuously at low power. This heats the food more slowly and evenly, preventing the formation of hot spots that can prematurely cook or ruin sensitive, sugar and fat-rich foods like meat, dairy, and desserts. In addition, inverter microwaves tend to be more energy efficient than traditional designs. Given their ability to cook meat and fish, it goes without saying that the microwaves produced by a magnetron are potentially dangerous to living tissue. Particularly vulnerable is the eye, which, having no cooling blood vessels of its own, is prone to overheating when exposed to microwaves, potentially resulting in the formation of cataracts later in life. Thankfully, the microwaves produced by a microwave oven are fully contained by the appliance's metallic cage, which acts as a Faraday cage named after the great English physicist Michael Faraday. Faraday cages exploit the fact that rapidly changing electromagnetic fields cannot penetrate a closed electrical conductor and are widely used to protect sensitive electronic equipment from external radio frequency interference, or RFI, or in this case, to prevent electromagnetic radiation from getting out. But the walls of a Faraday cage need not be solid, so as long as any openings are smaller than the wavelength of the radiation in question, said radiation will be effectively blocked. This is why the window in the door of most microwave ovens is covered in a fine metal mesh. Further safety is provided by a set of interlocking switches that prevents the magnetron from operating while the door is open. Thanks to these features, you can watch your microwave burrito spin around and around without fear of your face melting off. And of course, no discussion of microwave ovens would be complete without addressing the most taboo of household scientific experiments: putting metal in the microwave. The reason this is generally frowned upon is because metallic objects like forks and aluminium foil act like radio antennas, absorbing microwave energy and converting it into an electric charge. If the object in question has sharp edges, these will concentrate this electric charge, exceeding the breakdown potential of the surrounding air and throwing off lightning-like arcs called corona discharges that could potentially start a fire. Even worse, smooth metallic objects can reflect microwaves back at the magnetron, causing feedback that can ultimately overload and destroy the component, rendering the entire oven useless. Finally, absorbed microwaves can cause metallic objects to become extremely hot, posing a burn hazard. Indeed, this effect is sometimes exploited by manufacturers of microwave food. The packaging for pizzas, pies, and other items that would normally become soggy when cooked in a microwave often incorporate a thin metallic layer that absorbs and radiates heat back onto the food, creating a deliciously crispy crust. But unless you have a special microwave set aside specifically for mad scientific experiments, please take our advice: don't put metal in the microwave. Now, while radar sets and microwave ovens are the most common and famous applications for the magnetron, they are indeed far from the only ones. Indeed, high-powered microwave emitters are widely used in industry for applications as diverse as softening plastic before molding, drying potato chips, and roasting coffee beans and peanuts. And newer, more exotic applications are being discovered all the time. For example, in 2023, researchers at Australia's Macquarie University developed a method for using microwaves to selectively decompose the silicon in expired solar panels, allowing the other component materials like glass, plastic, and metal to be safely recycled. In the traditional recycling method, solar panels are crushed, heated to 1400 degrees Celsius, and treated with harsh solvents to dissolve away the plastic components, an energy-intensive and environmentally unfriendly process. Similarly, in 2022, researchers at Mitsui Chemicals in Japan announced a method for using microwaves to decompose polyurethane foam into its component chemicals without the use of toxic solvents. Meanwhile, a team at the Korea Electrotechnology Institute, or KERI, led by Dr. Sun-Shin Jung, has developed a device designed to bombard agricultural fields with microwave radiation, selectively killing pests hidden under the soil without the need for pesticides. Even more exotic engineers at Penn State University have devised a microwave-based method that could eventually be transported to the moon and used to smelt minerals found in the lunar dust or regolith, either to extract valuable metals like titanium or build permanent structures on the lunar surface. In the grand tradition of cheeky tech acronyms, the team dubbed their creation Smelting with Microwave Energy for Lunar Technology System for In Situ Resource Processing, or SMELT. From defeating the Nazis and Imperial Japan to making dinner time a bit more convenient to smelting metals on the moon, the cavity magnetron has come a long way and stands as one of the greatest stories of swords into plowshares in modern history. Now, if you'll excuse me, I think I'm going to microwave a burrito.